Okay, so today, if you've been following along with my series, I'm just kind of revamping on deep learning technologies that I think are going to be much more important in the coming future. I think a lot of the GPU programming um, is going to really be more of a requirement in a lot of places as we get more into these technologies. And so the first 2 days of this week, we were reviewing C++, Cuda kind of implementations and different people going over it. So today we're going to be kind of hitting the NVIDIA developer blog with my limited understanding of C++ from college and even worse because college didn't teach me much, kind of referencing the docs on that and going from there to try to understand what's happening. They do have, thankfully, they have notebooks that we can use, interactive ones. And so I'm going to be setting up an account. Actually, make sure I don't have an NVIDIA account already. I don't have an NVIDIA account. So I'm going to stop sharing my screen and create an NVIDIA account. And you should too, so that you can use some of their notebooks to learn on. Okay, now I gotta check my email. Okay, so hold on, let me finish setting it up. Okay, so I'm gonna enroll in this course and go back to here. So open collab. There we go, all set up. So we're gonna go through this notebook and the blog post, and I'm going to read and then execute. So we start with a simple C++ program that adds the elements of two arrays with a million elements each. So this creates the million elements to start top. So we include the math file, I remember that, IO string, remember that, function to add the elements of two arrays. So there's no built-in math. Oh, well, wait, there's built-in math, but you still have to call it. So here, this is an array, this is an array, right? And you add those together, iterate over it to get this one out. And it creates a million elements for each one, maybe. Iterate over the arrays in the host. Run the kernel, check for errors. Yes, important validating. And then free the memory. So first compile and run this program, but put the code above in a file and save it, okay? So that's what this notebook is for. And so if we run it compiled it. And this he compiled on a Mac. I'm guessing this is to compile on Google. And there's no errors when it runs this file because it's running in the command line, it looks like. Yeah, because the shell is running in the command line. So now we're going to run printer no error, right? And so you don't know repair. So first I have to run our add function into a function that the GPU can run called a kernel. So a kernel is a type of function GPUs run in Cuda. To do this, we have to do is add this global to the function, which tells Cuda C++ that this function runs on GPU and we got from a CPU code. So global runs GPU code from a CPU. And it base is a kernel, okay? And this is just what it means. Memory allocation. Let's see what they're talking about here. Yeah, it's following the blog all the way down. Okay, so to compute in on the GPU, I need to allocate memory accessible by the GPU. Unified memory. Oh goodness, why am I always so tired? Unified memory in Cuda makes it easy by providing a single memory space accessible for all GPUs and CPUs on your system. To allocate data in unified memory, call Cuda malloc managed, which returns a pointer that you can access from host CPU code or device GPU code. To free the data, just pass the pointer to Cuda free. Just need to replace the calls to the new in the code above with calls to Cuda like manage and replace all cells to delete. So this is talking about how it allocates to the memory and how it frees up the space. And to run it on the GPU, we need to invoke it using the triple angle bracket syntax. I just have to add it to the call. So this invokes this function that we created in this file, right? Yeah. So this runs it, but it invokes it. I don't get why we have 1 here. Let's see if we can figure it out. I wonder if my headphones are broken because that's annoying. I think I broke them. Easy. I'll get into the details of what goes on inside the angle brackets. Okay, great. For now, you need to know that this line launches one GPU thread to run. So it launches a GPU thread to run. And just one more thing. You need the GPU to wait until the kernel is done before it assesses the results, because CUDA kernel launchers don't block the calling CPU thread. To do that, we need to synchronize devices before doing the final error checking in the CPU. Okay, so kernel function, they create a kernel function, and they synchronize and wait for the GPU. They run the GPU thread. This is kind of initializing and allocating memory, checking for errors, free up memory, return. So it is for a single thread on the GPU. But since it's running in parallel, all the threads will be running the same function, which is how we get the speed. Right? Oh, it takes. They run this one. All right, so this gives us time with how long it takes to run that one thread, how much space it's taking up. And this is running in parallel. Okay. Now that you've run a kernel with one thread that does some computation, how do you make it parallel? The key is these triple angles. Syntax is called the execution configuration. It tells CUDA runtime how many parallel threads to use. So is that 3 parallel threads? That doesn't make sense. Keep reading. There are 2 parameters here, but let's start by changing the second one, the number of threads in a thread block. CUDA GPU run kernels using blocks of threads are multiples of 32 in size, and 256 threads is a reasonable size to choose. So one kernel with 256 threads, and that kernel size is 32. I think so. If I run the code with only this change, it will do the computation once per thread rather than spreading the computation across the parallel threads. To do it properly, I need to modify the kernels. CUDA C++ provides keywords that let kernels get the indexes of running threads. Specifically, thread index.x contains the index of the current thread within the blocks, and block dimension.x contains the number of threads in the block. So if we're reading this is the index of the thread. This is the threads in the block. Index of current threads in the block. Index and stride. So if I iterate start at the int equals the initial index. As long as the index is less than num, just the num we pass here, then 1 plus the stride, and then you add them. In fact, if you set index to 0 and the stride to 1, it makes it semantically identical to the first version. Yeah? Because so let's run that. And then run the speed, which did decrease our average times because they went from 1 thread to 256 threads. So this initially is 1 kernel with 1 thread, and it just incremented. But if you go 1 kernel with 256 threads, it spreads out until it completes the index. Out of the blocks, Cuda GPUs have many parallel processors grouped into streaming multiprocessors. Each streaming multiprocessor can run multiple concurrent thread blocks. As an example, a Tesla P100 GPU based on the Pascal GPU architecture has 56 streaming multiprocessors, each cable supporting up to 2048 active threads. Dude, to take advantage of these threads, I should launch the kernel with multi-thread blocks. But now, you may have guessed that the first parameter specifies the number of thread blocks. Together, the blocks of parallel threads make up what's known as a grid. Since I have n elements to process in 256 per block, I just need to calculate the number of blocks to get at least n threads. Oh, so much math, and not the type of math that I like. I simply divide n by the block size, being careful to round up in case n is not a multiple of block size. So they set the block size to 266 num blocks, so the num plus the block size minus 1 divided by block size, and that's how we now set our kernels and threads. So here, block index 2, 1, 2, dimensions 256, and you make 3 thread across 3 threads equals 515. So block index 0, 1, 2. So this goes from 0 to 2, 3, 1, 2, 3. Okay. So we need to update the kernel code to take into account the entire grid of thread blocks. Cuda provides grid dimension X, which contains the number of blocks in the grid, and the block index, which contains the index of the current thread block in the grid. Each thread gets its index by computing the offset to the beginning of the block. Okay. The updated kernel also sets stride to the total number of threads in the grid. Blocked in this type of loop in Cuda kernel is often grid stride loop. So this is building the grid that we're talking about with each component of the grid so that it can loop through available threads across each index block that is in the grid. Okay. So we have to really understand how many grids and how many grids and blocks we're working with in order to pace out um, okay, that makes sense, but let's look at the docs. Okay. So pretty much to understand how to code in CUDA, we need to understand concepts of kernels, threads, memories, blocks, grids, so that we know how to set it up how to properly define that to run our workflows on. And that's the confusing part because it doesn't operate like we would traditionally think about it. And that's just getting started with it. There's much more advanced. So let's start with the programming model. Okay. It's essentially, it's a section extension of C++, which explains, which I knew, but it also explains why C++ is popping back up into data science and machine learning engineering roles is in order to do this really well, understanding that it seems to be a prerequisite of some of the bigger companies. So they don't have to teach you C++ and you can get to this GPU programming sooner. Um, they explained what global and these kernels were in the other one. And so this one's just going back through it. This is the vector add function, which was in the example we did earlier too. And so I'm guessing this is the same code he defined before, but probably with, they have a whole repo of examples, which is great. Um, Probably with some caveats. So we have plenty of samples of different utilities. And I'm not about to go through all of this. I'm gonna get lost in the folder instruction. Okay. And then just building it a different way. I'm guessing that the original post was in 2017. I'm guessing this is an updated. Um, this one's updated in. Yeah, this is like version 12.5, so much more updated. Here, I want to go here. Now, thread. I wonder if we're going to always have to separately define this. I guess yesterday when we were looking at Jeremy Howard and how he integrates into PyTorch, that is probably going to make this much simpler some of the time at the very least. So this is talking about the grid and the blocks. Again, it looks like it's just going back through it. But you can cluster your blocks and your threads together. Yeah, this is going to be the most complicated part. It's like, how do you actually code the architectures of running it across the GPU? And you're going to have to stare at this for a long time. And like run, I don't know, simple implementations of stuff in it. Documentation is not bad at all, actually. I don't know, my mind is not happy with having to think like this. Let me think back through this clustering thing. Okay, so a thread block cluster is enabled in a kernel either by using a compiled time kernel or using actually best practices. Okay, it doesn't seem to have it. Yeah, this is more of what I'm worried about. It's applying it with the shared memory space. I'm not sure how that. I guess I need to worry about clusters at the moment. I need to understand shared memory in the context of Cuda. Okay, so each thread would be responsible for computing the softmax of a unique subset of thread elements. They each still loop over the entire input array twice to find the max value and compute it, and instead use shared memory to store. Okay. So while each thread can run the process, if we put the constant information into shared memory, we won't have to iterate over those arrays. And this is just it just gives us bigger things to run on. Okay. Let's skip around. I wonder, how do I choose like which of these libraries to use? And I'm also just kind of writing down questions I have so I can go look for them later or tomorrow. Because I have questions about like shared memory, different packages, and when to use them. How do you like optimize it to run the model so that's not running on one thread, like in between PyTorch and Cuda? Like they were talking about the softmax problem. Actually, let me bookmark this handy dandy blog. Um, that'll be helpful. Where's the best practice? These are so many libraries. I'm not about to go through that. I will get too confused if I start here. So we're going to get out of that. So much on it. Okay, where's back here? So, do I actually need to pay attention to heterogeneous computing? I'm not going to. Let's say that. I don't think we're going to get into that this week. I get it as an overhead, but I'm not a hardware developer. I'm not sure if it actually matters when I'm building models as of yet. When we go through the thing tomorrow. Yeah. How do you actually optimize it if you have to go between devices? So maybe it is important. I don't think it's going to be a concept I'm going to understand this week. Because it seems complicated because I have to understand the compute times and speeds and how you check that, like if you're in the middle of coding. I would say let's get into notebooks tomorrow. But if you haven't optimized your code, you don't want to scale it. So I don't think I need to get into scaling architectures. But this would be, I'm going to bookmark this best practice guide for later use. I actually probably need to make a Cuda specific bookmark. Because it feels like this is going to quickly get complicated. So this creates the kernel, which we know. Kernels define the behavior of one single thread. Yeah, I think running through several of these demonstrations until I can understand threads, blocks, kernels, grids really well would be the best use of time. Okay. So, I hate having to look at code that I've never looked at before in the evenings because I'm a morning coder. I rather wake up at 5 and code till 10. I'm dead in the afternoon and I'm not going to be code available till it's bedtime. And I'm going to sleep at bedtime. I hate that. I feel like weird things about developers. I can't develop all day. Like, I can understand this stuff at certain times of the day pretty well. And the rest of the time, I am useless. So I need to do my research for my organization or during the rest of the time. Okay. Fascinating. Hmm. Fascinating. Okay. That's going to be the most cool folder dedicated to research on applied AI. So cool. Okay. So I think we're going to start here tomorrow and I'm going to end early and get my brain ready to read this code because it's like reading it, but it's not understanding it. And I feel like I'm like semi-interpreting the languages. If I can't visualize what I mean, I might need to do. There was another suggestion of doing GPU puzzles, but it's in Numba. I kind of didn't want to learn in Numba. Number, 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 number. I might have to though. I might have to because I'm not visualizing it in my mind. Let me bookmark this. Okay, so I need to. I think I'm gonna end up doing the puzzle so I can visualize it. Which isn't great because I do need to know Cuda. I don't need to run it in Python, but maybe this will help get the visualization down and then I can convert it into C++ syntax. I think so. Okay, I will see you guys tomorrow. Thanks for tuning in. We're going to try this again then.